The following is a free-for-download audiobook available on Google Drive. Origins Magazine, Higher Dimensions in Science. Big questions about the Big Bang. When examined closely, the cosmologists' confident explanations of the origin and structure of the universe falls apart. Look up at the night sky, full of stars and planets. Where did it all come from? These days, most scientists will answer that question with some version of the Big Bang theory. In the beginning, you'll hear, all matter in the universe was concentrated into a single point at an extremely high temperature, and then it exploded with tremendous force. From an expanding superheated cloud of subatomic particles, atoms gradually formed, then stars, galaxies, planets, and finally life. This litany has now assumed the status of revealed truth. In accounts that deliberately evoke the atmosphere of Genesis, the tale of primal origins is elaborately presented in countless textbooks, paperback popularizations, slick science magazines, and television specials, complete with computer-generated effects. As an exciting, mind-grabbing story, it certainly works. And because the Big Bang story does seem to be based on factual observation and calculations, a Big Bang model with irregularities in the distribution of matter on the observed scale must still have a singularity in the beginning. The question of origins. The problem of the singularity is simply part of the larger problem of understanding the origin of the initial condition of the universe, whatever it may have happened to be. If a model of universal origin involves a singularity, that certainly creates severe theoretical difficulties. But even if the singularity can somehow be avoided, we are still confronted with the question of where the universe came from. Hoping to sidestep the whole issue of origins, some scientists have proposed the so-called infinitely rebounding universe. A universe that expands, contracts into a singularity, and then again expands and contracts continually through the course of unlimited time. There is no beginning and no end, only an endless cycle. This resolves the problem of the origin of the universe by proposing that there is no origin and that the material universe has always existed. But there are some serious problems with this model. First of all, no one has ever proposed a satisfactory mechanism for the bouncing. Furthermore, in the first 3 minutes, physicist Steven Weinberg points out that with each successive bounce, progressive changes must take place in the universe. This indicates that at some point there must be a beginning and not a regress extending over an infinite period of time. Thus again, you confront the question of origins. Another creative attempt to escape the necessity of dealing with the question of origins is the time reverse rebounding universe model proposed by English astrophysicist Paul Davies. The universe would expand, with time flowing forward, and then collapse into a singularity. During the rebound, time flows backward as the universe expands, and it collapses again into a singularity, the same singularity from which it began its previous forward cycle. In this model, the past becomes the future, and the future becomes the past, thus making the statement, quote, "in the beginning," meaningless. This scenario gives one small indication of the many imaginative schemes the cosmologists have been forced to resort to in order to explain the origin of the universe. The inflationary universe. Quite apart from the question of where the initial condition of the universe comes from, there are other problems troubling modern cosmologists. In order for the standard Big Bang theory to predict the distribution of matter we observe within the universe, the initial state has to be fine-tuned to an incredible degree. The question then arises, How did the initial state get that way? Physicist Alan H. Guth of MIT has proposed a version of the Big Bang model that automatically produces the required fine-tunings, doing away with the necessity of artificially introducing them into the equations. Called the inflationary model, it assumes that within a rapidly expanding superheated region of the universe, a tiny section cools off and then begins to expand much more violently, just as supercooled water rapidly expands when it freezes. It is this phase of rapid expansion that resolves some of the difficulties inherent in the standard Big Bang theories. But Guth's version has difficulties of its own. Guth has been forced to fine-tune his own equations in order to get them to yield his inflationary universe. Thus, he's confronted with the same difficulty his model was supposed to overcome. He'd hoped to explain the fine-tuning required in the Big Bang universe, but he requires unexplained tuning of his own. Guth and his collaborator, Paul J. Steinhardt, admit that in their model, quote, calculations yield reasonable predictions only if the parameters are assigned values in a narrow range. Most theorists, including both of us, regard such fine-tuning as implausible, end quote. They go on to express a hope that in the future mathematical theories may be developed that will enable them to give a plausible expression to their model. This dependence on a yet unrealized future development highlights another difficulty with Guth's model. The grand unified theories, GUTs, upon which the inflationary universe are based, are completely hypothetical and, quote, have little support from controlled experiments because most of their implications are impossible to measure in the laboratory, end quote. The grand unified theories are very speculative attempts to tie together some of the basic forces of the universe. Another problem with Guth's theory is that it does not even attempt to explain the origin of the superheated expanding condition necessary for his inflation to take place. He has toyed with three hypothetical origins. The first is the standard Big Bang. According to Guth, the inflationary episode would take place within the very early stages of it. This model, however, leaves us with the knotty singularity problem already discussed. The second option is to assume an initial condition of random chaos, in which some regions would be hot, others cool, some expanding, some contracting. The inflation would begin in an area that was superheated and expanding. But Guth admits that there is no explanation for the origin of the imagined primordial random chaos. The third alternative, favored by Guth himself, is that the superheated expanding region emerges quantum mechanically from nothing. In an article that appeared in 1984 in Scientific American, Guth and Paul J. Steinhardt state, quote, the inflationary model of the universe provides a possible mechanism by which the observed universe could have evolved from an infinitesimal region. It is then tempting to go one step further and speculate that the entire universe evolved from literally nothing, end quote. As attractive as this idea may seem to scientists who balk at any suggestion of a supreme intelligence that designed the universe, it doesn't hold up under close examination. The literal, quote, nothing, end quote, Guth is speaking of is a hypothetical quantum mechanical vacuum state occurring in a still-to-be-formulated ultimate grand unified theory combining the equations of both quantum mechanics and general relativity. In other words, this vacuum state cannot now be described, even theoretically. However, physicists have already come up with a description of a simpler kind of quantum mechanical vacuum state, which can be visualized as containing a sea of, quote, virtual particles, end quote, atomic fragments that almost, but not quite, exist. From time to time, some of these subatomic particles pop up out of the vacuum into material reality. Such occurrences are called vacuum fluctuations, The fluctuations cannot be directly observed, but theories based on them have been corroborated by laboratory experiments. What theoretically occurs is that a particle and antiparticle appear without cause from the vacuum and almost instantaneously negate each other and disappear. Guth and his colleagues postulate that instead of just a tiny particle, the entire universe popped out of the vacuum. And instead of instantaneously disappearing, our universe has somehow persisted for billions of years. The singularity problem is avoided by having the universe pop into being a little beyond the stage of singularity. There are two basic shortcomings in this scenario. First, it involves a truly impressive speculative leap from our limited experience with subatomic particles in the laboratory to the universe as a whole. Stephen Hawking and G.F.R. Ellis sagely warned their colleagues who would, without hesitation, hurl themselves headlong into such wild speculation. Quote, "There is, of course, a large extrapolation in the assumption that the physical laws one determines in the laboratory should apply to other points of space-time where conditions may be different." End quote. Second, it is actually misleading to speak of the quantum mechanical vacuum as, quote, "literally nothing," end quote. To describe a quantum mechanical vacuum, even the relatively simple one of currently existing theory, requires chapters upon chapters of highly abstract mathematics. Such an entity is certainly, quote, "something," end quote, and this raises the interesting question of where such a complicated, quote, "vacuum," end quote, might come from. At this point, let us return to the original problem Guth was trying to solve with his inflationary model, trying to eliminate the need for fine-tuning initial conditions in order to obtain the observed universe. As we have seen, he hasn't succeeded. But another problem is this: does any version of the Big Bang Theory, including Guth's, really predict the observed universe? What Guth says he finally gets out of his complicated initial state is a universe about 4 inches across, filled with nothing more than a uniform, superdense, superheated gas. This will expand and cool, but there is no reason to suppose that it will ever become more than a cloud of uniformly distributed gas. In fact, this is all that any of the Big Bang theories leave you with. So, if Guth's present theory requires implausible tinkering simply to yield a universe consisting of uniformly distributed gas, then we can just imagine what would be necessary to get it to yield the universe as we know it today. In good scientific explanation, many complex phenomena can be deduced from a single theoretical scheme. But in Guth's inflationary universe, and indeed in the standard Big Bang theories, we have just the opposite. From a very complex tangle of equations, we just get an expanding uniform ball of gas. Despite this, science magazines run articles about the inflationary model, complete with pages of high-tech illustrations that give the impression Guth has finally achieved the ultimate goal, explaining the origin of the universe. Not quite, it seems. Perhaps they should run regular columns in the science magazine featuring the universal origin theories of the month. We can just imagine the complexity of the initial conditions necessary to produce the universe as we know it, with all its varied structures and organisms. In our own universe, these conditions seem to have been arranged far too precisely to be explained by simple physical laws. Thus, one could argue, conceivably, in favor of a designer. At this point, some noted theorists take shelter of what they call, quote, the anthropic principle. They propose that the quantum mechanical vacuum is producing universes by the millions. The great majority are not constituted so as to produce life. These universes therefore do not contain observers who could study their conditions. However, other universes, including our own, are constituted so as to have produced observers, and it is therefore not surprising that these observers would discover that their universe possesses some rather startlingly precise conditions to allow the existence of life. According to this line of reasoning, the observers should not expect to find anything other than such improbably complex conditions. In fact, supporters of the anthropic principle take the very existence of human beings as the explanation of why the universe is so constituted as to have produced human beings. But this logical sleight of hand isn't an explanation of anything. Another form of verbal jugglery is to say straight out, as many scientists do, that the universe has occurred by causeless chance. Chance and the origin of the universe. Some scientists are using the concept of chance that in a way that misleads the public. Unable to explain the origin of the universe by physical laws, they assert that it was somehow caused by chance. But such statements are not meaningful. To make any statement about a chance event meaningful, many repetitions of the event in question are required, and these must be observable. For example, we can flip a coin many times and note the results. We can see that they correspond to a statistical pattern indicating a 50% probability that heads will turn up rather than tails. The word chance, therefore, does not actually refer to a cause. It refers only to a certain type of pattern in the results of an operation repeated a sufficient number of times. Upon recognizing such a pattern, we can say, quote, there is a 50% chance that the toss coin will come up heads, end quote. Now, imagine that we could toss a given coin only once and it came up heads. If someone asked why that result happened, we may give a causal explanation or say that we don't know, but it would not be meaningful to say it happened by chance. So now, what about the universe? It is not possible for us to observe more than one appearance of the universe. We can only see the one we're in. The origin of the universe is thus a one-time event, and statements about it that involve chance are meaningless according to the rules of quantitative science. Nonetheless, some theorists continue to speak of universes emerging from quantum mechanical vacuum by chance. To be quite frank, this is another limitation of quantum mechanics which is based upon the concept of chance. It may be valid to apply chance to events that can be repeated and observed in the laboratory, but in the case of the universe, where such repetition and observation are impossible in principle, chance is meaningless. Thus, it is useless to attempt to use quantum theory to explain the origin of the universe. One might imagine a hypothetical trans-universal being who can observe the origin of many universes and compute statistics about them, thus rendering statements about the chance origin of universes meaningful. But how could we obtain such information unless we could actually communicate with this being? This is tantamount to saying that there is a God and that we can communicate with him about the origin of the universe, a possibility modern science rejects. It must be pointed out that this idea of the universe occurring by causeless chance is not at all an explanation. To say that something happens once by chance is in essence no different than simply saying, quote, it happened, end quote, or, quote, there it is, end quote. And these statements do not qualify as scientific explanations. In the end, you wind up knowing no more than you did before. In other words, by invoking either chance or the anthropic principle, the scientists have not actually explained anything about the origin of the universe. At this point, the theorists could perhaps forgive us for suggesting that their chosen methods might not be quite adequate for the task at hand. Indeed, it appears, in addition to the problems that we have already discussed, that general relativity and quantum mechanics, the two intellectual tools with which the cosmologists are attempting to define the development of the universe, contain certain flaws. It is true that relativity in Einstein's earlier theory of special relativity is that they rule out time as we commonly understand it. In Newtonian physical laws, or physics, time is treated as a variable separate from space. In this way, it is possible to chart the path of an object moving in space and time in the following way. At a particular point in time, the object is located at a particular point in space. As time varies, the position of the object in space varies. But in Einstein's theory of relativity, this conception evaporates. Instead, time and space are wedded together in a four-dimensional space-time continuum. It is no longer possible to describe an object as occupying a particular point in space at a particular point in time. A relativistic description of an object will show its spatial and temporal existence in its entirety, merge from beginning to end wherever it is happening. For instance, a human being would be depicted as the entire progression from embryo to corpse. Such constructs are labeled, quote, space-time worms, end quote, and physics does not permit the space-time worm to say, quote, now I am adult and I used to be a child, end quote. There is no passage of time. The whole sequence exists as one unit. If we are space-time worms, if we are just configurations of matter, not personalities with consciousness, defining human beings in that way, and validates our individual perception of past, present, and future, and thus leads to the conclusion that such perceptions are unreal. In a letter to Michael Besso, Einstein wrote, quote, you have to accept the idea that subjective time, with its emphasis on the now, has no objective meaning, end quote. When Besso died, Einstein tried to console his widow by writing, quote, Michael has preceded me a little in leaving this strange world. This is not important. For us who are convinced physicists, the distinction between past, present, and future is only an illusion, however persistent, end quote. This is, in effect, a denial of consciousness, which entails the rationality or the reality of the present experienced moment. We experience our present form as real, whereas our infant form exists only in memory. As conscious beings, we can definitely experience that we do occupy a particular bodily form at a particular point in time. Despite the fact that relativity theory converts a series of events into a single unified spatio-temporal entity, we can actually experience in sequence different points in time. What all this means is that every theory of universal origins built around relativity theory fails to explain our conscious experience of time, thus making these theories as they stand incomplete and unacceptable. Quantum physics and reality. All the current cosmological theories also depend on quantum mechanics, which defines the activity of atomic and subatomic particles. Quantum physics differs in fundamental ways from classical Newtonian physics. Classical physics concerns itself with the behavior of solid matter, but quantum physics is concerned only with mathematical expressions of observations and measurements. Solid material reality evaporates. Nobel laureate physicist Werner Heisenberg declared, quote, it turns out that we can no longer talk of the behavior of the particle apart from the process of observation. In consequence, we are finally led to believe that the laws of nature which we formulate mathematically in quantum theory no longer deal with the particles themselves, but with our knowledge of elementary particles, end quote. In addition to the experimental apparatus, the observer had to be brought into the analysis as an explicit element distinct from the apparatus. But there are fundamental problems in applying quantum mechanics to the universe. By definition, the universe includes all observers, so you cannot have an outside observer of a universal physical system. In an attempt to formulate a version of quantum mechanics that does not require an outside observer, eminent physicists such as John Wheeler have proposed that the universe continually splits into innumerable copies. Each parallel universe contains observers to see that particular set of quantum alternatives, and according to this theory, all of these universes are real. Reacting to this, Bryce D. Witt, writing in Physics Today, states, quote, "I still recall the shock I experienced on first encountering the multi-world concept. The idea of 10 to the 100th plus slightly imperfect copies of oneself, all constantly splitting into further copies, which ultimately become unrecognizable, is not easy to reconcile with common sense. Here is schizophrenia with a vengeance," end quote. If scientists want a Big Bang theory of the origin of the universe that can be consistent with quantum mechanics, this is one of the bizarre hypotheses they are forced to come up with. But even more problems lie ahead on the path of materialistic reduction that most scientists are treading. It is bad enough that both general relativity and quantum mechanics lead to bizarre and unrealistic consequences when applied to cosmological questions. But these difficulties are compounded to an exasperating degree by the fact that scientists' hopes to properly describe the universe and its beginning depend on combining both theories. The proposed result would be a grand unified theory, GUT, capable of describing all the forces at work in the universe by a single comprehensive mathematical expression. General relativity is required to explain the basic structure of space-time. Quantum mechanics is needed in order to explain the behavior of subatomic particles. Unfortunately, these two theories apparently contradict each other. The first step toward this mathematical integration is quantum field theory, which attempts to describe the behavior of electrons by a combination of quantum mechanics and Einstein's theory of special relativity. This theory has scored some remarkable successes. Yet, P.A.M. Dirac, the Nobel Prize-winning English physicist who invented the theory, confessed, quote, "It seems to be quite impossible to put the theory on a sound mathematical basis," end quote. The second and much more difficult step would be to combine general relativity with quantum mechanics, and no one has the faintest idea how to do this. No less an authority than Nobel laureate Steven Weinberg admits that it may take a century or two to get the mathematics together. The cosmologists say they need the GUT to describe the origin of the universe, and they don't have it yet. So that can only mean their Big Bang and inflationary models are without solid foundation. Since the days of Newton and Galileo, the program of physical science has been to express everything in mathematical terms. Furthermore, the mathematical description must be confirmed by observation and controlled experiments. We have shown that the Big Bang theories fail to conform to these requirements. Simplicity has also been stressed as a requirement of physical theories, and the Big Bang theories also fail in that respect, for they are becoming, as we have seen, progressively more outlandish and contorted with each new formulation. They are just what Galileo and Newton would have disliked, storytelling to fill in the gaps of knowledge. The Big Bang theories would therefore appear to be something less than actual scientific explanations of the origin of the universe. Nevertheless, in popular magazines and television specials, as well as in the classroom, scientists deliberately give the public the impression that they have already succeeded in demonstrating exactly how the universe originated simply by physical laws. Nothing could be further from the truth. what about galaxies? We have seen that the cosmologists' attempt to comprehend the universe within the narrow bounds of their narrow materialistic conceptions has failed to explain its origins. Moreover, we have seen that their theories do not even account for what they say is present in the universe now. For instance, the Big Bang Theory does not account for the existence of galaxies. Imagine a scientist of great genius who had knowledge of current cosmological theories but no knowledge of observational astronomy. Would he be able to predict that galaxies would form? The answer is no. A universe made up of a uniformly distributed cloud of gas is the only result consistent with the standard formulations of the theory. This cloud would have the density of perhaps one atom per several cubic feet, making it little better than a perfect vacuum. To get anything else requires special modifications of the initial conditions of the universe, and scientists find such modifications difficult to justify. Traditionally, a scientific theory is acceptable if, starting from the original framework, you can straightforwardly predict things. A theory that has to be monkeyed around with to a considerable degree to obtain valid predictions is of questionable value. As Steven Weinberg says in the first 3 minutes, quote, "The theory of the formation of galaxies is one of the great outstanding problems in astrophysics, a problem that today seems far from a solution," end quote. But then, without skipping a beat, he says, quote, "But that's another story," end quote. But no, wait a minute. That is exactly the story. If the Big Bang Theory can't explain the initial cause of the universe or major features of the universe, such as galaxies, then what does it explain? Not very much, it would seem. Missing mass. The Big Bang Theory is supposed to explain the universe, but a major problem is that many features of the universe are not clearly understood enough to be the subject of such explanation. One big mystery is the problem of missing mass. Physicist David Schramm of the University of Chicago explains, quote, "From all the light being emitted by the Milky Way, we can estimate that a galaxy contains the mass of about 100 billion suns. But once we take this same object, the Milky Way, and see how it interacts with another galaxy, such as our neighbor Andromeda, we find that our galaxy is gravitating toward Andromeda as though it had a mass almost 10 times as great," end quote. Thus it appears that over 90% of the mass of the universe is missing. Ghostly subatomic particles called neutrinos have been put forward as the solution. Originally, however, the invisible neutrino was assigned no mass, but physicists now it has suddenly been assigned a mass sufficient to account for the missing mass of the universe as a whole. How convenient. But even when we leave aside the question of primal origins and get down to the picture of the universe as it is today, there are still many unanswered questions. The scientists will assert to the public with an air of absolute conviction that they know the universe extends X millions of light years and it has existed for a total of Y billion years. They say that they have identified all the major bodies of the universe for what they are: distant stars, galaxies, nebulae, quasars, and so forth. Yet even the local Milky Way galaxy is not clearly understood. For example, in Scientific American, noted astronomer Bart J. Bach wrote, quote, "I remember in the mid-1970s as a time when I and my fellow Milky Way watchers were notably self-assured. We did not expect that there would soon be a necessity to revise the radius of the Milky Way upward by a factor of 3 or more and increase its mass by a factor as much as 10. If such basic measurements recently had to be drastically revised after so many decades of observation, then what might the future hold? Will there be even more drastic revisions?" Even when we get down to our own solar system, we find that there are fundamental problems. The traditional account for the origin of the planets, that they have condensed from clouds of cosmic dust and gas, is on very shaky ground, but because the equations for the interactions of the gas clouds have never been satisfactorily solved. William McRae, professor of astronomy at England's Sussex University and past president of the Royal Astronomical Society, states, quote, "The problem of the origin of the solar system is perhaps the most notable of all unsolved problems in astronomy." It should be clear at this point to any impartial onlooker that the strategy of materialistic reduction followed by the cosmologists has not allowed them to arrive at a firm conclusion about the nature and origin of the universe despite their public posturing. There is certainly no compelling reason for anyone to insist that the ultimate answers to cosmological questions must be contained in simple, mathematically expressed physical laws. Indeed, the quantitative method has proved inadequate for explaining many phenomena very close at hand, what to speak of explaining the vast universe. Therefore, it is certainly too early to exclude alternative approaches that may involve non-physical explanations involving principles that go beyond the known laws of physics. A different picture of reality. There may be, in fact, non-physical causes at work in the history of the universe, and there may be even non-physical regions of the cosmos as well. Physicist David Bohm admits, quote, "The possibility is always open that there may exist a wide variety of additional properties, qualities, entities, systems, levels, etc., to which apply correspondingly new kinds of laws of nature," end quote. Thus, it is quite possible that our understanding of natural laws continue to evolve. A picture of reality quite different from the one people now accept may emerge. As we have already seen, with infinitely rebounding and infinitely splitting universes, some of the models and concepts proposed by the cosmologists already challenge our common sense conception of things. Do not think that these strange ideas are out of the mainstream of scientific thought. All the notions we have considered so far are actually the most staid and respectable speculations. Now, let us look at some even more outlandish ideas currently running loose in the world of modern cosmology. Scientist John Gribben, author of White Holes, a book summarizing these topics, admiringly calls them, quote, "the latest series of imaginative leaps made by the creative thinkers today we call scientists, rather than prophets, seers, or oracles," end quote. One is the white hole, a quasar that pours out galaxies in a cosmic gusher. Gribben says, quote, "Could the white holes actually fragment themselves so that galaxies would reproduce themselves like amoebas by parthenogenesis?" That sounds so unlikely in terms of our everyday experience of the behavior of matter that it's worth looking at the standard theories of galaxy formation to show just how hopeless they are in explaining explanations of the real universe. Visioning white holes might seem like a solution of last resort, but when no other theory produces any kind of satisfactory solution, that solution is surely the one we must accept, end quote. Another idea seriously entertained by cosmologists is space-time tunnels, or, quote, "cosmic wormholes," end quote. First seriously discussed in 1962 by physicist John Wheeler in his book Geometrodynamics, the idea has entered into popular consciousness through fantasy movies such as the Star Wars series, where starships hurtle through hyperspace, making intergalactic journeys that would normally take millions of years at the speed of light. Some versions of the wormholes see them as entrances into the past and future, or even into other universes. In the earlier part of this century, Einstein posited a fourth dimension. Now, as the implications of his gravitational field equations are being more fully explored, extra dimensions are being added. Paul Davies, a theoretical physicist, writes, quote, "In addition to the 3 space dimensions and the 1 time dimension we perceive in daily life, there are 7 extra space dimensions that have hitherto gone unnoticed," end quote. The point of these descriptions is to show that even the material scientists are being compelled to put forward explanations of the universe that stretch the mind to an incredible degree. But must we stretch our minds only in the directions pointed out by material science? Perhaps our minds can be stretched in even other directions. If we can contemplate higher material dimensions, then why not dimensions of an entirely different sort? There is an definite need for a new category of ideas that need that will undoubtedly challenge the currently held reductionistic scientific strategy for understanding the universe. That strategy includes the idea that the universe is ultimately simple and can be exhaustively described in terms of quantitative laws. But suppose that this isn't so. It certainly appears that the universe is unlimitedly complex and has aspects that may not be approached by quantitative methods. If so, what strategy can be used to gain knowledge about it? The many complex and orderly features of the universe suggest that its cause is an intelligent designer. This idea brings to mind the following possible strategy. If the underlying cause of the universe is a supreme intelligent being, then there is hope that we can understand the ultimate nature of reality by obtaining information from this being. That there is such a being is certainly a bold proposition, but no more so than the proposal that everything can be explained by simple mathematically expressed physical laws. And just as in the case of quantitative strategy, the value of this alternative strategy can only be judged by how successful it can be applied. It would be unfair to reject it without seeing how well it can be used to gain practical knowledge about reality. To many, the idea of a supreme intelligence will bring to mind the worldview of Christian fundamentalism, which many people have varying reactions. But alternatives to the current theories of cosmologists are not limited to the fundamentalist Christian interpretation of Genesis. Just as there are many possible materialistic explanations of the origin of the universe, there are many possible explanations involving a personal creator. For those seeking to broaden their intellectual options, one very rich source of ideas for understanding the cosmos and our place in it is the Vedic knowledge of ancient India. The Vedas include some extremely sophisticated cosmology. Some of the concepts will be radically different from those now being propagated. Others will be surprisingly complementary with current scientific findings. For example, Carl Sagan, while in India filming a segment for his Cosmos television series, said, quote, "The most sophisticated ancient cosmological ideas come from India. Hinduism, based on the Vedas, is the only religion in which time scales correspond to scientific cosmology," end quote. He noted that the sages of ancient India held that the universe undergoes progressive cycles of creation and destruction over time scales lasting billions of years. As in modern science, the basic unit of matter is the atom, in Sanskrit, the anu. But the Vedas also include particles of consciousness called jivatmas, as well as an integrated superior conscious principle called the paramatma, supersoul. The supreme being, seen as the source of the variety of the physical and universal energies, is described as a personality simultaneously omnipresent and localized, in whom the universe exists and who exists within every atom of the universe. As we shall see throughout this magazine, such ideas are give a more complete and coherent understanding of the origin and nature of the universe. Consciousness, in particular, is a fundamental aspect of reality that cannot be ignored in theories that attempt to comprehensively explain the cosmos. At a time when scientists are proposing such things as multiply splitting universes, cosmic wormholes for traveling from one space-time region to another, universes in which time reverses, an 11th dimension of space-time, etc., the ancient transcendental conceptions found in the Vedas should not be dismissed without due consideration. The Big Bang and inflationary models, which rest on the shakiest of mathematical and theoretical foundations, have certainly failed to provide adequate answers to fundamental questions about the universe and the galaxies and planets and life forms we find within it today. Perhaps a superconsciousness, a supremely intelligent designer, and not a set of impersonal mathematical equations, is the ultimate explanation for the universe that now seems so inexplicable.